This video is for the notes that you will be given on Thursday, January 29th. In this guided notes page, we see that there are two ways that you can communicate electron configurations. We've been working on the first one, orbital notation, which, if you remember, looks like this over here. Okay. Now, this type of notation for electron configuration is very tedious, and it takes up a lot of space, and it's a lot of time drawing in all those arrows, and so we know that there just has to be a better way to do this. So, good news is there is, and it's called electron configuration notation. As you can see here, that's listed as 2A, and that's what we're going to focus on in this video. For 2B, the shorthand electron configuration notation is something that we'll learn next week. So just as a reminder of what orbital notation is, remember we were using these lines to represent orbitals, and then we use the arrows pointing up and down to represent electrons. And how we represented these on orbitals, so an orbital that contains only one electron would be represented by just putting one arrow on that line. And if an orbital contains two electrons, we had to then follow Pauli's rule, which states that electrons could only occupy the same orbital as if they have opposite spins. Okay, so we've done many examples of this orbital notation. Let's just do one for carbon. So carbon on the periodic table has an atomic number of 6, so we know that it's going to contain 6 electrons. So if we draw in our own diagram, since one's not supplied here, we know that we still have to follow Aufbau's rule. So Aufbau says that we have to start with our electrons and putting them in the lowest energy level, which would be the 1s. So I'm going to come over here, I'm going to write in 1s, and then put my one line for my 1s orbital, which I can then fill with my 2 electrons. Okay, so I've used 2 of the 6. I still need to represent 4 more electrons in this picture. So again, after the 1s comes the 2s. And 2s has higher energy than the 1s, so I'm going to write it above it, put my little line there, and then draw in my 2 electrons. So I've represented 4 of my 6 electrons. After the 2s, we then draw in the 2p. Well, 2s and 2p are the same energy level, so I'm just going to represent them here next to each other. And 2p then has 3 orbitals with it because there's 3 possible orientations in space for the p orbital. Okay, so I've already represented 4 electrons. I only need to represent 2 more in order to make 6. So I place 1 and 2 to make sure that I follow Hund's rule, which states that I have to put 1 electron on each orbital until there's too many, and then I pair them up. Well, since we only have 6, we ran out when we reached here. But even though this is empty, we're still not breaking Hund's rule because we didn't pair these 2. We've just ran out of electrons. So that's as far as we can go. All right. Now on to this idea of a better way of representing these without all these lines and building these huge diagrams. We use electron configuration notation. Okay, so there are some parts to this notation. As you can see represented here, we still want to show the information like that was supplied in the orbital diagrams. So we're still going to be using this language of quantum numbers, where we'll represent that with kind of like what looks like a coefficient in math. We're still going to use our letter notation for orbital shape, where we'll use S's, P's, D's, and F's. But instead of drawing all the lines and all of the arrows, what we're going to do is say that on this energy level and in this orbital, how many electrons are there? So we can see here this is the 1s, and the 1s holds 2 electrons, which over here we've represented as a superscript number 2, instead of drawing those arrows. So let's take this diagram here, and then translate this diagram into what carbon's electron configuration would look like. So we're going to do this for carbon. Okay. Now Aufbau's principle still applies here. Okay, so we have to start our configuration with the lowest energy, and as we move from left to right, we're going to get to higher and higher and higher energies. So according to Aufbau, of course, as we know, we have to start with the 1s, then the 2s, and then the 2p. So I'm going to list those orbitals out, just like I have here. I have my 1s, my 2s, and my 2p. So if I list those out, I have my 1s orbital, my 2s, and my 2p. I'm going to look at this picture and I'm going to count in the 1s how many electrons are there. Well, there are 2. So I come back over here and I put a superscript of 2. In my 2s orbital, again there are 2. 2. And in the p orbital, I also have only 2. So yes, 6 electrons can fit on the p orbital, but we're not writing what's possible, we're writing what is there. And in the carbon orbital diagram, there are 2 electrons on the first 1s orbital, and there are 2 electrons in the 2s orbital, and there are 2 electrons in the 2p orbital. Just like we can see again here in this example. So this is a much better way of representing these electron configurations. It takes up way less space and a whole lot less time to write it like this. In my next video, I'm going to go through our past homeworks, and we're going to translate all those orbital diagrams into this electron configuration. And then eventually we're going to start to make connections between these electron configurations and the periodic table, so that hopefully, just by looking at where an element is located on the periodic table, you'll be able to know what its electron configuration should be. All right, so in the next video, make sure you have your document number 8 ready to go so that we can translate out those orbital diagrams into electron configurations. Thanks.